Welcome back to Think Thrice Problem Solving. Today we're going to be solving a really awesome problem. So we're going to be solving for the nth term in the Fibonacci sequence. So if I plug in n equal 120, we should be able to immediately solve using our equation for the 120th term without figuring out all the intermediate terms. Okay, so just to remind you what a Fibonacci sequence is. So if we have the first two terms, f sub 0 and f sub 1 are equal to 1, then every term after that is going to be the sum of the previous two terms. So what does that mean? That means f sub 2 would be 1 plus 1, which is 2. F sub 3 is 2 plus 3, which is 5. F sub 4, sorry, 2 plus 1, which is 3. F sub 4 would be 2 plus 3, which is 5. F sub 5 would be 3 plus 5, which is 8, and so on and so forth. Okay, so I'm going to post, or I already posted a previous video. I'll put a link in the description. But what we did before is we looked at this problem and we figured out by creating an ordinary generating function. So an ordinary generating function is basically a function where we have a sum with this power series, x to the n, where the terms, the coefficients, are our Fibonacci sequence. So the Fibonacci sequence represents this a sub n here. So when we did that, we would start off with f sub 0 times x to the 0, which is 1. And then we'd have f sub 1, which is 1 times x to the 1. And then we continue to have this expression. And I'm going to kind of breeze through this because I have another video that goes through this process. But what we do is we then take this guy and we recognize that f sub n is f sub 1 n minus 1 plus f sub n minus 2. And then we change indices to get what is our original function in two different spots, so here and here. And then we solve for this f of x. So we solve for this ordinary generating function here to get an analytic solution. Okay? And this is not going to be convergent to a lot of values of x, but that's okay, because when we're using ordinary generating functions, what we're concerned with are the coefficients. Okay, so as I said, I'm not going to go into too much detail about that, but it was a fun little video that you can go back and watch. But what we're going to do now is we've already established now that this summation, so this power series with the Fibonacci sequence as its terms, the coefficients, is equal to this equation on the left. And I'm going to use that to solve for these nth terms of the Fibonacci sequence. So what we're going to do is we're going to rewrite this guy as negative 1 over x squared plus x minus 1. And then we're going to do some work here with this fraction. So we're going to do some partial fraction decomposition. So in order to do that, I need to know what my roots are of this. So my roots are going to be x is negative 1 plus or minus the square root of b, which is 1 minus 4ac, so plus 4 over 2, which is going to give me negative 1 plus or minus the square root of 5 divided by 2. So what I'm going to do is I'm going to say a is going to be equal to negative 1 plus square root of 5 over 2. And I'm going to have b equal to negative 1 minus square root of 5 over 2, just because I don't want to keep writing those numbers down over and over. Okay, so using partial fraction decomposition, I'm going to say that negative 1 divided by x squared plus x minus 1 is then going to be equal to something over x minus a plus something over x minus b. And I guess I'm going to make these c and d just so I don't have to keep saying same letters and confuse people. Okay, so using partial fraction decomposition, I'm going to go ahead and multiply these through. So c times this plus d times this is over this times this. And remember, x minus a times x minus b is going to be equal to x squared plus x minus 1. So what we're going to do is I'm going to take c times x minus b plus d times x minus a and that whole thing is going to be over x minus a, x minus b, is going to be equal to negative 1 over x squared plus x minus 1. And what does that mean? That means that cx plus dx is going to be equal to 0 times x. And the reason I'm saying 0 times x is there's no x terms up here. So what does that tell me? That tells me that c is equal to negative d. And then I'm going to look, so that was the x to the 1 terms. Now I'm going to take the x to the 0 terms. So if I look at the x to the 0 terms, I now have negative c times little b plus d, or minus d, times little a is equal to negative 1. So using what I already determined, so using the fact that c is equal to negative d, I have d times b minus d times a is equal to negative 1. So that d times b minus a is equal to negative 1, which gives me d is equal to negative 1 over b minus a. I want to remember what b minus a, what b and a were. So b and a are these two guys up here. Negative 1 plus or minus square root of 5 over 2. So I'm going to rewrite this now as negative 1 divided by, and then I had negative 1 minus square root of 5 over 2 minus, what color was that? Purple. Negative 1 plus square root of 5 over 2, which is then going to be equal to negative 1 divided by, got a few things that are going to cancel out, so this negative 1 and this negative 1 are gone. And so I have negative root 5 over 2 minus root 5 over 2, so that's negative 2 root 5 over 2. So a few more things are going to cancel, so these negative signs are gone, these 2's are gone, and I'm going to be left with just 1 over the square root of 5. And then immediately I know c is equal to negative d, so if d is equal to 1 over the square root of 5, then c is equal to negative 1 over the square root of 5. So let's remember the whole purpose of why we were doing this. So the reason I did this is now I have negative 1 over x squared plus x minus 1 is equal to negative 1 over square root of 5 divided by x minus a plus 1 over square root of 5 divided by x minus b. So I have a new solution here for my Fibonacci ordinary generating function. All right, so now the next step we're going to do is we're going to look at Taylor series. Okay, so what Taylor series say is if I have some function, then that's equal to the sum from n equals 0 to infinity of, and this isn't always true, it's not always convergent, but at infinity it generally be okay. So we're going to take the nth derivative. Sorry, that's not a true statement what I just said. So yeah, so it won't always converge, okay, but that's not important when we're doing ordinary generating functions. So what we're concerned with are, once again, the coefficients. So f sub n, or the nth derivative of f evaluated at 0, so this is technically a Maclaurin series, times x to the n. Okay, and so if we do this for our different guys, so this first one, if we have negative 1 over square root of 5 times x minus a, 1 over x minus a. So if we do that, that's going to be negative 1 over the square root of 5. And then for that second part, when we go through this, we're going to end up taking the derivatives, and ultimately what we'll end up with is the sum from n equals 0 to infinity of 1 over a to the n plus 1, and this is negative, times x to the n. Okay, and that's if we go ahead and execute this Taylor series equation. So I'm skipping a little bit of a step there. Similarly, if I look at 1 over square root of 5 times 1 over x minus b, that's going to end up giving me 1 over the square root of 5 times the sum from n equals 0 to infinity of negative 1 over b to the n plus 1th power times x to the n. Okay. So why is this important? So why is this even useful? So you'll notice that now I have terms that are now written as power series for each of my two up here. So I have these two guys both written as power series, and they were equal to my analytic solution for my Fibonacci ordinary generating function, which in turn was equal to this guy up here, okay, which is also another power series. So this is the trick we're going to use here. So I'm going to pull down this power series up here, and what we're going to see is that I have the sum from n equals 0 to infinity of this Fibonacci term times x to the n is going to be equal to, and remember it was equal to this guy, which is equal to -1 over square root of 5 times the sum from n equals 0 to infinity of -1 over a to the n plus 1 times x to the n plus 1 over square root of 5 times the sum from n equals 0 to infinity of -1 over b to the n plus 1 times x to the n. Okay, and what I'm going to do now is I'm going to move this guy in. So I'm going to have my negatives cancel here. Also going to move this guy in. And I'm going to rewrite this as the sum. I'm going to combine sum now. So this is the sum from n equals 0 to infinity. And notice both of these have an x to the n term. So I'm going to pull all the factors. And this is going to be 1 over the square root of 5 times 1 over a to the n plus 1 minus 1 over b to the n plus 1 times x to the n. Okay, so essentially what we've just done is I now have two different versions of a power series. So I have a power series on the left where my coefficients are the terms in the Fibonacci sequence. So this is my Fibonacci sequence. And over here I have these other equations which are all in terms of that a and b term, which I know what those numbers are. And I notice that my indices are all the same. And I have this x to the n, so this is supposed to be to the nth power. Sorry, I wrote that as x of n for some reason. So now what that tells me is that the f sub n, which is my Fibonacci, my term in my Fibonacci sequence, is then going to be exactly equal to 1 over square root of 5 times 1 over a to the n plus 1 minus 1 over b to the n plus 1. Okay, so now looking at our equation here, we can do a little bit of math to kind of clean this up. So this is going to be equal to 1 over square root of 5 times b to the n plus 1 minus a to the n plus 1 over a times b to the n plus 1. Okay, let's figure out what a times b is. So a times b is -1 plus square root of 5 over 2 times -1 minus square root of 5 over 2. So these are conjugates. So remember, if I have to use different letters here. Let's see, w plus v times w minus v is going to be equal to w squared minus v squared. So what does that tell me? That this is going to be equal to 1 minus 5 divided by 2 times 2, which is 4, which is going to be -1. So what I'm going to end up here is a times b to the n plus 1 is going to be equal to -1 to the n plus 1. So I can pull that out, and I'm going to end up with -1 to the n plus 1 over square root of 5 times b to the n plus 1 minus a to the n plus 1. Okay, and then I can multiply through, and I'm going to end up getting 1 over square root of 5 times b times -1, so negative b to the n plus 1 minus negative a to the n plus 1. So what does that tell me? This f sub n, so my Fibonacci term, is going to be equal then to 1 over square root of 5, and then negative b, so what was b and what was a? So b going all the way up. So b is negative 1 minus square root of 5 over 2, and a is negative 1 plus square root of 5 over 2. So I'm going to end up with I'll just go ahead and write it out. So negative 1 minus square root of 5 over 2 to the n plus 1 minus negative, so we're got to make sure my parentheses, so negative 1 plus square root of 5 over 2 to the n plus 1. And then finally, my equation for the nth term in the Fibonacci sequence is going to be 1 over the square root of 5 times 1 plus square root of 5 over 2 to the n plus 1 minus 1 minus square root of 5 over 2 to the n plus 1th power. And that is going to be my final solution. So if I've worked everything out correctly, if I want to find, say, the 120th term of the Fibonacci sequence, I would just plug 120 in for my n. So remember, we just plug something in for n, and that's going to give us our nth term. So assuming that we're starting at n equals 0, so n equals 0 and n equals 1, we're going to give us f sub 0 and f sub 1 equals 1. The rest of our numbers are going to be here. All right, so I hope you enjoyed working through this with me. I hope this might be the first time you've seen this, but I think it's a fun problem and it's a fun little exercise with a bunch of different math topics involved. If you enjoyed this video, please like and subscribe. If you have your own problem that you'd like me to do, please submit your idea to thinkthriceproblemsolving@gmail.com. And as you're working through problems on your own, think once, think twice, and if you ever get stuck, think thrice.